students, welcome to chemistry class. Today I'll be teaching a chapter from inorganic chemistry. The chapter name is D and F block elements. Let's get started. So this is the periodic table. So in the last year you have studied about the S block elements as well as the P block elements. So that is why in this year you will be studying about the remaining two blocks, that is D and F block elements. So here the elements of first two groups, they are collectively called as the S block elements, and the elements belonging to group 13 to 18, they are called as the P block elements. Comes the D block elements. The elements belonging to the group 3 to 12 are collectively known as D block elements. And here we have F block elements, which has two series. So one is the lanthanide series, other is the actinide series. Lanthanide series, it starts from the element lanthanum and ends with the lutetium, whereas the actinide series of elements starts with actinium and ends with the lawrencium. So then, how do we define D block elements, or what are D block elements? Here it is, the definition. The elements of the periodic table belonging to group 3 to 12 are known as D block elements. In the previous slide, so I have shown you the D block elements. So the elements of the periodic table belonging to group 3 to 12 are known as D block elements. And why they are called so? Because in these elements the last electron enters into D subshell or D orbital, hence these elements are called as D block elements. Let's move on to the next slide. And what are F block elements? So here the definition is like this. The elements in which 4f and 5f orbitals are progressively filled in the two long periods. So in the previous slide I have shown you. So F block elements contains two series. One is the lanthanide series of elements, other is the actinide series of elements. In the lanthanide series of elements, 4f orbital is progressively filled. So here you know that in any f orbital, maximum we can accommodate 14 electrons. So here in the lanthanide series, 4f orbital it is progressively filled, and in case of the actinide series, 5f orbitals are progressively filled. Now I'll show you which are the F block elements. Here you can see there are two series. One is the lanthanide series, other is the actinide series of elements. Lanthanide series, it starts from lanthanum, ends with lutetium, and actinide series of elements, it starts from actinium and ends with the lawrencium. So here in this slide, so you can make out which are the D block elements and which are the F block elements. So the elements of elements belonging to group 3 to 12, so they are collectively known as D block elements. And then we have a separate block, that is F block, which has two series. One is the actinide series and other is the lanthanide series of elements. And then here I have taken the first transition series of elements, which starts from scandium, ends with the zinc. And here here we have mentioned the atomic number, atomic symbol of the first lanthanide, first transition series of elements, and their respective electronic configuration. So here you can see scandium, whose atomic number is 21, has electronic configuration as argon core 3d1-4s2, whereas titanium, whose atomic number is 22, has electronic configuration argon core 3d2-4s2, and so on. So here what you can make out, what you can understand, so here in these elements 3d orbital, it is progressively filled. So that is why, so this first transition series of elements, they are also called as 3d transition series of elements, because in these elements 3d orbital is progressively filled. Here there are four transition series of elements. So the first transition series, second transition series, third transition series, and fourth transition series of elements. The first transition series of elements, it includes the elements from scandium to zinc. So in the previous slide I have shown you. So here the first transition series elements, they are also called as 3D transition series of elements, because in these elements 3d orbital, it is progressively filled from 3d1 to 3d10. Here, second transition series, which is also called as 4D transition series, includes the metals from yttrium to cadmium. Here, why it is called as a 4D transition series of elements? It is because in these elements, 4D orbital, it is progressively filled from 4d1 to 4d10. Next series is third transition series, which is also called as 5D transition series of elements, which include the elements from hafnium to mercury. And here in this series of elements, 5D orbital is progressively filled. The last one is the fourth transition series, which is also known as 6D transition series of elements. This series includes the elements from Rutherfordium to Copernicium. Here 6d orbital is progressively filled. So D block has 4 transition series of elements. They are first, second, third and fourth transition series. They are also called as, like, first transition series is called as 3D transition series of elements, because here in these elements or in this series 3D orbital is progressively filled. So similarly, second transition series is called as 4D transition series, because here in this series of elements 4D orbital is progressively filled. Then third transition series is called as 5D transition series of elements, because in this series of elements 5D orbital is progressively filled. And the last one, fourth transition series, so which is also called as 6D transition series of elements, because in these elements 6D orbital is progressively filled. So this is about the different series of transition elements in the D block. So here in this slide you can make out. So here the first transition series, that is also called as 3D series. So it includes the elements from scandium to zinc. So similarly, the 4D transition series, so which is the second transition series of elements. So it ranges from yttrium to cadmium. And then the third transition series, which is known as 5D transition series, so which includes the elements from hafnium to mercury. Then what is the general electronic configuration for D block elements? So I think in the last year you can remember, with respect to the S block and P block elements, you had written the general electronic configuration, particularly for S block elements and for P block elements as well. So here also for the entire D block elements, so we can give a general electronic configuration, and it is like this: n-1d 1 to 10, ns 1 to 2. So here, what is this n-1d 1 to 10 and ns 1 to 2? So here, why we have mentioned d 1 to 10? So you know that in any d orbital, we can accommodate maximum 10 electrons, or you can say the maximum capacity of d orbital is 10 electrons. So here, in this series of elements, d orbital, it is progressively filled from 1 to 10 electrons. Whereas here, ns refers to the outermost s orbital, and you know that in any s orbital maximum we can accommodate 2 electrons. That is why we have mentioned ns 1 to 2. So here, what is n-1d here? It is the inner d orbital. So where n-1d refers to inner d orbital and ns refers to the outermost s orbital. And here, between these two energy level, that is n-1d and ns, there is a little energy gap. The energy gap, energy difference, or little energy gap can be seen between n-1d orbital and ns orbital, or you can say there is a little energy difference between n-1d and ns orbitals. So here, how to prove that? So how do we come to know that the energy gap between n-1d and the ns orbital is little? So to prove that, so here I have taken 2 examples. I have taken the elements of the first transition series, that is from 3D series. I have taken 2 elements, one is chromium and other is copper. Now we shall see. The actual electronic configuration of chromium is given as argon core 3d5 4s1. But So if we follow the rule, see here, both chromium and copper, they are going to violate the actual rule for assigning electrons in various shells of an atom. See, the actual electronic configuration of chromium is argon core 3d5 4s1 instead of argon core 3d4 4s2. So why we state like this? See, according to the rules for assigning electrons in various shells of an atom. So here, while accommodating the electrons, how do we follow? First, we fill the energy levels with lower energy first. Later, so we fill the electrons in the orbitals with the higher energy level. So when we compare the energy difference with respect to 3d and 4s orbital, so 4s orbital is the orbital with lower energy and 3d orbital is the orbital with higher energy. So as per the rule, first we have to fill the 4s orbital and then the remaining electron will go to the 3d orbital. So here when we do so, then we obtain the electronic configuration of chromium as argon core 3d4 4s2. But as I said earlier, the energy difference between 3d and 4s orbital is so small. So because of which, so here what happens now, you shall see, the energy gap between 3d and 4s orbital is small enough to prevent the electron entering the 3d orbital. So that means an electron will be shifted from 4s orbital to the 3d orbital. So thereby the electronic configuration of chromium becomes argon core 3d5 4s1 and not argon core 3d4 4s2. So similarly, I'm going to take one more example. So in case of copper, its electronic configuration is written as argon core 3d10 4s1 and not as argon core 3d9 4s2. See, when we fill the 4s orbital first, after that we allocate the remaining electrons in the 3d orbital. When we follow that rule, then we obtain the electronic configuration for copper as argon core 3d9 4s2. But since the energy gap is small between 3d and 4s orbital, an electron will be shifted from 4s orbital to the 3d orbital. So thereby we are going to obtain the electronic configuration for copper as argon core 3d10 4s1. Now you carefully observe both the cases, both chromium as well as the copper. So one electron is being shifted from 4s orbital to the 3d orbital. In case of chromium, so we had seen, so when there is a shift of one electron from 4s orbital to the 3d orbital, we have obtained the electronic configuration as argon core 3d5 4s1. So you know that in d orbital maximum 10 electrons can be accommodated, right? So then what we have obtained here 3d5, which is the exactly half of its capacity. What I mean to say here, chromium has got half filled 3d orbital. So when there is a shift of electron from 4s orbital to the 3d orbital. Similarly, in case of copper also, the same shifting of 4s orbital, so shifting of an electron from 4s orbital to the 3d orbital can be seen. So thereby here we have obtained completely filled 3d orbital. So then why this kind of shifting of electron takes place? Because if any element, if it is having a half filled and completely filled sets of orbitals, it is considered to be stable, or you can say it is going to attain the stability by having a half filled and completely filled sets of orbitals. So that is why in case of chromium, in order to obtain stability, one electron will be shifted from 4s orbital to the 3d orbital so as to obtain a electronic configuration as argon core 3d5 4s1, where 3d orbital is half filled. That is why chromium is going to be more stable. So similarly, in case of copper, when one electron is being shifted from 4s orbital to the 3d orbital, so here we are going to obtain a completely filled 3d orbital, which leads to more stability. So in either of the cases, the shifting of electron from 4s orbital to 3d orbital is being done in order to obtain stability. So in any element, so if it is having a half filled and completely filled sets of orbitals, it is going to be relatively more stable. Transition elements. So here the definition for transition element is like this. A transition element is defined as the one which has incompletely filled orbital in its ground state or in any one of its oxidation states. See, if you want to call any element belonging to D block as transition element, it should necessarily have an incompletely filled D orbital. Then only it can be called as a transition element. So a transition element should have partially filled or incompletely filled n-1 d orbital. Then only it can be called as transition element. Okay, so here, and there is one more reason. So why d block elements are called as transition elements? If you look at the periodic table where they have occupied which place, d block elements are called as transition elements because they occupy the middle of the periodic table and their properties are transitional between S block and P blocks. So what I mean to say, here in the periodic table, D block elements occupy the middle position of the periodic table, that is in between the S block elements and the P block elements, and they also possess the properties possessed by both the S block and P block elements. That is why we have used the term. Their properties are transitional between S block and P block elements, hence they are called as transition elements. Then, now the question is, can we call all the elements present in the D block as transition elements? The answer is no, because here we have an exception. Zinc, cadmium and mercury, they are not at all regarded as transition elements, though they have been included in the D block. Now, let's see what is the possible reason for that. The electronic configuration of zinc, cadmium and mercury are represented by the general formula n-1 d10 ns2. Carefully observe here. So n-1 d10 refers to having completely filled d orbital. ns2 also refers that the outermost s orbital is also completely filled. So now if we have a careful look towards the electronic configuration of zinc, cadmium and mercury, now we will come to know that here zinc, whose atomic number is 30, having electronic configuration as argon core 3d10 4s2, cadmium, whose atomic number is 48, having its electronic configuration as krypton core 4d10 5s2, and mercury, whose atomic number is 80 and its electronic configuration is xenon core 5d10 6s2. So here, if you carefully observe the electronic configuration of these three elements, so one thing we will find out. What is that? Having completely filled d and s orbitals. So that is why, so here the general electronic configuration for these three elements, it is written as n-1 d10 ns2. Now let's go back to the previous one. What is that? So if you want to call a D block element as transition element, what is the necessary condition? The necessary condition is it should have partially filled or incompletely filled d orbital. But here what we have got with respect to zinc, cadmium and mercury, all these three elements they are having completely filled d orbital, so which is exactly contrary to the actual statement for the transition elements. That is why all these three elements they are not regarded as transition elements, but still, so they have been included in the D block elements, and we have to study about these three elements along with the study of D block elements, because their chemical and physical properties, they are very similar to transition elements. So that is why, so we are going to study about zinc, cadmium and mercury physical and chemical properties along with the remaining D block elements. Remember, all these three elements, since they have got completely filled d orbitals, so they are not regarded as transition elements. Then let's pass on to the physical properties of transition elements. See, all these elements which are included in D block, they are metallic in nature. That means the first property says that all are metals. All the D block elements, they are metallic in nature, or you can say they are metals. These are malleable and ductile, except mercury, which is a liquid. So here these metals can be made into sheets and wires. That's what the meaning is. Next property. So they have high tensile strength. Tensile strength is resistance of a material to breaking under tension. Suppose if you want to break a material, how long it can show resistance, that is called as tensile strength, and all these transition elements they have high tensile strength. And they have high thermal and electrical conductivity as well. That means they are very good conductors of heat and electricity. And they have metallic luster. So in your lower classes we have studied that all the metals they have shining surface, that is the metallic luster. And they are sonorous. That means, so here capable of producing a ringing sound. So you might have heard the bell ringing in the church or in the temples. It is just because those metals which are used to make that bell, so they are sonorous in nature. Lastly, transition metals are very hard and they have high melting points and boiling points. It is due to the strong metal-metal bonding which exists between the metal atoms. Trends in melting points of transition metals. Here is a graph, atomic number versus melting point. So here we have taken the first, second and third transition series of elements and we have plotted a graph. So if you carefully look at the graph, so what we can infer, melting point and boiling point of transition metals increases from left to right here. So look at the third transition series from hafnium to, here it is the gold. So here you can see from left to right it keeps on increasing, becomes maximum in the middle of each series and then decreases except in case of the manganese and technetium. So here you can see there is a dip in the melting point of technetium and manganese. Or in other words we can say manganese and technetium, they have low melting points because see both have having the a larger number of unpaired electrons, but remember these electrons they do not get delocalized. That means they cannot move freely, so because of which they cannot form strong metal bonds. That means when they fail to form strong metal bonds, then it will be easier to break the bond which exists between the atoms. That is why we will see a dip or a decrease in the melting points of technetium and manganese. Melting point and boiling point of second and third transition series are higher because of stronger metal-metal bonds. So as the atomic number increases, the availability of the number of unpaired electrons increases, which leads to the formation of strong metal-metal bond. That is why the melting point and boiling point of second and third transition series are higher because of stronger metal-metal bond. Enthalpy of atomization. So here it is defined like this. The amount of energy required for the conversion of a metallic crystal into individual atoms is called enthalpy of atomization. So I repeat, the amount of energy required for the conversion of a metallic crystal into individual atom is called enthalpy of atomization. So suppose suppose if we have a metallic crystal like this, okay, one more. This is a metallic crystal and here the dots represent either the atom or the ions. So there will be in any metallic crystal there will be regular arrangement of atoms or ions. So here what is the amount of energy required to break this metallic crystal into individual atoms? So for this purpose what is the amount of energy required is called as enthalpy of atomization. Are you able to understand? So here we have a metallic crystal. In order to break up this metallic crystal into individual atoms, what is the amount of energy required? That's what the statement says. The amount of energy required for the conversion of a metallic crystal into individual atom is called as enthalpy of atomization. So here, the transition metals have high enthalpy of atomization. It is attributed to the strong interatomic interactions with greater number of unpaired electrons results in stronger bonding. What does it mean? It means that if the metal atoms offer a more number of or larger number of unpaired electrons, that leads to strong interatomic interaction. That means the bond which exists between the metal atom, it becomes more and more stronger. That is why if we want to break a metallic crystal into its individual atoms, then definitely we have to supply a large amount of energy. That is why we say transition metals have high enthalpy of atomization, because so as we move down the series, like from first transition series to the second transition series of elements and second to third, so what happens? The availability of the number of unpaired electrons increases, which attributes the strong interatomic interactions, which leads to the formation of strong metal-metal bond. That is why all transition metals, they have high enthalpy of atomization. Second and third transition series of metals have greater enthalpy of atomization because of stronger metal-metal bonding. So why they form stronger metal-metal bonding? It is due to the availability of the greater number of unpaired electrons, which results in the formation of stronger metal-metal bonding. Atomic and ionic radii. So about which you have already studied when you were in first year. I'm just putting some pictures just to rebrush your memory. So here, this is the atomic radii and its definition, and also we have ionic radius. See, closely you just have a look at these pictures. Here, atomic radius, the definition is half of the distance between nuclei in covalently bonded diatomic molecule. So here in the first picture, so we have a diatomic molecule, so where two atoms, they are bonded to one another. So here you can see what is D? D is the distance between the two nuclei of covalently bonded diatomic molecule. So here, what is R? Atomic radius, D by 2, half of the distance. That's what the definition says. Half of the distance between the nuclei in covalently bonded diatomic molecule is called as atomic radius, which is given by R is equal to D by 2. So D is the distance between the two nuclei, half of it, that is D by 2, is the atomic radius. Similarly, the half of the distance between the nuclei of two ions is called as the ionic radius. Now, let's come back to the D and F block elements. Atomic and ionic radii of transition metals are smaller than the corresponding S block elements. See, last year actually we have studied in inorganic chemistry that when we move from left to right in the periodic table, the atomic and ionic radii of the elements is found to be decreasing. So here, so when we say it decreases, so when it comes to the D block elements, the atomic and ionic radii of transition metals are usually smaller than the corresponding S block elements. Atomic and ionic radii of transition metals show progressive decrease along the period. So when we move along the period in the D block, so we will see a considerable decrease in the atomic and ionic radii. Then what must be the reason for this? From left to right in a transition series, atomic number increases. Okay, so what happens if the atomic number increases? If the atomic number increases, what is the definition for atomic number? It is the number of protons present in the nucleus of an atom. See, in any atom, so as to maintain the electric neutrality, so there will be equal number of protons and the electrons. If the number of protons are increasing, consequently, that increases the number of electrons in the penultimate shell. So number of protons in the nucleus and the number of electrons in the penultimate shell also increases. Penultimate shell means the shell or the energy level which lies just before the outermost shell. It is called as penultimate shell. So in which we will see increase in the electrons. And remember, these electrons have to be accommodated in the inner d orbitals after filling the outermost s orbital. But d electrons have poor shielding effect or poor shielding power. Thus, effective nuclear charge increases. See, when there is increase in the number of electrons in the d orbital, But we will see the d electrons have got poor shielding effect. That means the electrons present in the d orbital cannot overcome the force of attraction exerted by the nucleus. Or in other words, we can say these electrons, they are under the influence of force of attraction exerted by the nucleus, which we call it as effective nuclear charge, which is going to get increased because of the poor shielding power of electrons present in the d orbital. So nuclear attractive force on the outermost electron increases as a result of the poor shielding effect of d electrons. So the effective nuclear charge increases, and hence atomic and ionic radii decreases. See, the electrons present in the d orbital, when they fail to overcome the force of attraction exerted by the nucleus, so they are greatly pulled by the nucleus towards itself. That leads to decrease in atomic and ionic radii. And so that was the story about the atomic and ionic radii along the period. What happens down the group? Atomic and ionic radii down the group increases from first to second transition series of elements, but the atomic radii of second and third transition series are virtually same. So when we move from first transition series to the second transition series, we will see considerable increase in atomic and ionic radii. But as we move from second to third transition series of elements, their atomic and ionic radii, they are almost same. What is the reason? The reason is very simple. The similarity in the radii is due to the filling of 4f orbitals before 5d orbitals, which causes a phenomenon called as lanthanide contraction. To understand this, let us take two examples. So here I have taken hafnium and the tungsten. Hafnium, whose atomic number is 72 and its electronic configuration is xenon core 4f14 5d2 6s2, and on the other hand we have tungsten, whose atomic number is 74 and its electronic configuration is xenon core 4f14 5d4 6s2. See here, both the elements have got completely filled 4f orbitals. So here, look at the previous statement. So why there is a similarity in with respect to the radii of second and third transition series of elements? It is due to the filling of 4f orbitals before 5d orbitals. So here, until and unless 4f orbital is completely filled, no electrons go to the 5d orbitals. So what I mean to say, first 4f electron is get completely filled, thereafter the remaining electrons goes to the 5d orbital. So this actually causes lanthanide contraction. So then what is this lanthanide contraction? See, lanthanide contraction is actually seen in case of the lanthanides. So already actually I have shown you. So when I have shown you the picture of periodic table, F block elements means, so it has two series, lanthanide series and actinide series. Just look at the lanthanide series of elements. It starts from lanthanum, ends with the lutetium. When we move from lanthanum to lutetium, we will see gradual and steady decrease with respect to the atomic size of the lanthanides. So this phenomenon is known as lanthanide contraction. The same can be seen in the third transition series, so which is due to the filling of 4f orbital before 5d orbital, which is the actual reason for the lanthanide contraction. The definition of lanthanide contraction is like this: steady decrease in the size of lanthanides with increase in the atomic number is known as lanthanide contraction. Same phenomenon can also be seen in case of the third transition series of elements. That is why their atomic number, their atomic size is found to be resembling very much with the second transition series of elements. Trends in atomic radii of transition elements. Here, we have plotted a graph here with atomic number versus metallic radius, and we have taken the first three transition series of elements. The first transition series, that is the 3D series, second transition series, that is 4D series, and third transition series, it is 5D series. So already actually have come to know that when you move from first transition series to the second transition series, there is a considerable increase in the atomic radii. But look at the green dots and red dots. They are almost very close to one another. That means the atomic radii of second and third transition series are virtually same. That's what the graph says. Density. How do you define density? It is mass by volume, right? Here, from left to right in the periodic table, the atomic radii decreases where atomic mass increases. See, in any period, so when you move from left to right, what happens to the atomic radii? Actually, it decreases. So when atomic radii get decreased, that leads to the increase in the atomic mass. Remember, in mass by volume ratio, if mass is increasing means what? Density should also increase. So what I mean to say, from left to right in a period, atomic radii decreases where atomic mass increases, thus density increases. Next is valency and oxidation state. Transition metals show variable oxidation state. The general electronic configuration of transition elements can be written as N-1 D1 to 10, Ns 1 to 2. Already you are familiar with by now. All the transition metals show divalency, that is valency 2, and +2 oxidation state in common using Ns electron. So look at the general electronic configuration. N-1 D 1 to 10 refers to inner d orbital and Ns refers to outermost s orbital. So all these elements, they readily lose the electron present in the outermost s orbital. Thereby, they are going to have valency as 2 and oxidation number as +2. They may show higher valency and oxidation state by successive use of N-1 d electrons. So just actually we came to know that when they lose the electrons present in the outermost s orbital, they are going to acquire oxidation state as +2 and divalency as 2. Then after losing the electrons from outermost s orbital, there are electrons in the inner d orbital which they can lose so as to increase their valency as well as the oxidation state. Then oxidation states of 3D transition series of elements. So here you can see the oxidation states of first transition series of elements, so which starts from scandium, ends with the zinc. So here what we can infer, oxidation state increases from left to right up to manganese with the increase in the number of unpaired electrons. See, if we have a closer look towards the oxidation states of the first transition series of elements, so here you can see +3 for scandium, +4 for titanium, and for vanadium it is +5, and here you can see from scandium to manganese it keeps on increasing because the availability of number of unpaired electrons keeps on increasing, and it becomes maximum when it reaches manganese. Then after manganese it keeps on decreasing because there is a decrease in the availability of number of unpaired electrons. So that is why we see decrease in the oxidation states of the first transition series of elements after manganese. And here what we can infer, so from this chart here, so manganese is the element of first transition series which is having highest oxidation number. So this is important for 1 mark. So they may ask us which element in the 3D transition series has highest oxidation number. The answer is manganese, which is having a +7 as its oxidation number and which is maximum for the first transition series. Stability. Here, the stability of higher oxidation state is maximum in the middle because in the beginning of the series there are fewer electrons to lose or share, and at the end there are fewer orbitals available for sharing of electron. See, so in the previous slide I had shown you, so manganese was the element which is having the highest oxidation number, and it is going to be the most stable also. It is because it is in the middle, and also it is having the maximum number of unpaired of electrons. So here the stability that depends on the availability of the number of unpaired electrons, because when there is availability of the larger number of unpaired electrons, that leads to the sharing or losing of electrons, which leads to the stronger bond formation so as to attain the stability. That is why it states that stability of higher oxidation state is maximum in the middle, because in the beginning of the series there are fewer electrons. So in case of the scandium, so only 3 electrons were available. That is why its oxidation state was only +3. So in the beginning, from scandium to manganese, so there are fewer electrons are available for the bond formation, and after manganese again there are fewer orbitals available for sharing of electrons. That is why the stability is at its maximum only when it comes to manganese. Stability of higher oxidation state increases down the group, that is from top to bottom, because the distance of d orbitals from the nucleus increases, removal of electrons becomes easier. See, when you move down the group, that is from one transition series to the other transition series, the stability increases. Why? Because the distance between the nucleus and the electrons present in the d orbital keeps on increasing. Then it becomes very easy to remove the electrons from the outermost shell or from the d orbital. Hence, that leads to the stability. Okay, so that's it for today. So let me stop here. We will meet in the next class. Thank you. Welcome to Inorganic Chemistry class, chapter D and F block elements. In the last class, we have discussed about the some properties of interstitial elements of D block. Stability was the last topic, so I'll continue from there. Next property is ionization enthalpy. Ionization enthalpy is the amount of energy required to remove an electron from the outermost shell of an isolated neutral gaseous atom. That means if we want to remove one electron from the outermost shell of an isolated neutral gaseous atom, what is the amount of energy required for that purpose is called as ionization enthalpy. Ionization enthalpy increases along the series of transition elements, that is from left to right. So when we move along any transition series, we see that ionization enthalpy increases along the series. Why? Because when we move from left to right in any period, atomic radii decreases as the effective nuclear charge increases. So if an effective nuclear charge increases, the force of attraction exerted by the nucleus on the outermost electron increases. Then we require more energy in order to remove electron from the outermost shell of such element. What happens to the down the group ionization enthalpy? Down the group ionization enthalpy decreases. This is because down the group atomic number increases, the distance between nucleus and the electrons present in the outermost shell keeps on increasing. Then it becomes very easy to remove electron from the outermost shell of these elements. Hence, down the group ionization enthalpy decreases. Irregular trend in the first ionization enthalpy of 3D metals is due to irregularity in electronic configuration of 4s and 3d orbital. When we look at the first ionization enthalpy value of 3d series of elements, there we see irregularity in the ionization enthalpy. First ionization enthalpy means the amount of energy required to remove first electron from the outermost shell of an atom. It is called as first ionization enthalpy. So if you look at the first ionization enthalpy of 3D transition series of elements, we see irregular trend can be observed, and this is due to irregularity in the electronic configuration of 4s and 3d orbital. If you remember in previous class, we have discussed about the electronic configurations of chromium and copper. So they are not going to follow the APA principle. So there is a clear violation, and there was a transfer of one electron from 4s orbital to the 3d orbital in order to obtain stability. So since there is irregularity in the electronic configuration, we also see irregular trend in the first ionization enthalpy. The second ionization enthalpy is always higher than the first ionization enthalpy. So just naturally I told you that first ionization enthalpy is the amount of energy required to remove first electron from the outermost shell of an atom. So then after the removal of first electron, the effective nuclear charge on the remaining electrons increases. What I mean to say, the force of attraction exerted by the nucleus on the outermost electrons increases. As a result of this, if we want to remove the second electron from the outermost shell, we need to supply more energy than the first ionization enthalpy. That is why second ionization enthalpy is always greater than first ionization enthalpy. And so with respect to the third ionization enthalpy, the amount of energy required to remove the third electron from the outermost shell is called as third ionization enthalpy. So in case of 3D transition series of elements, so here once they lose the electrons present in the 4s orbital, then the third electrons has to be removed from the inner 3D orbital, which requires a lot of energy. So that is why third ionization enthalpy is always very high, because the third electron is to be removed from the inner d orbital. If you remember the general electronic configuration of d block elements, it is n-1 d 1 to 10 ns1 to 2. So after losing both the electrons present in 4s orbital, the third electron has to be removed from the inner d orbital, which actually requires a lot of energy. This second ionization enthalpy of copper is very high. You will always get this kind of questions with respect to the ionization enthalpy. Second ionization enthalpy of copper is very high. Why? So the answer is very simple. So first, you need to understand why second ionization enthalpy of copper is very high. So here I have mentioned the ground state electronic configuration of copper, whose atomic number is 29. So its electronic configuration can be written as argon core 3d10 4s1. It is easy to remove an electron from 4s orbital, but the second electron is to be removed from the stable 3d10 orbital, which requires high ionization energy. Hence, second ionization enthalpy of copper is very high. See, once we remove the electron present in the 4s orbital, then the second electron has to be removed from the most stable completely filled 3d orbital. So here we require a lot of energy. That is why second ionization enthalpy with respect to copper atom is always very high. Here you can see. So once it loses one electron present in the 4s orbital, then the second electron has to be removed from this completely filled 3d10 orbital, so which requires lot of energy. So that is why second ionization enthalpy of copper is very high. Next important property of transition metals is magnetic properties. So when a magnetic field is applied to substances, mainly two types of magnetic behaviors are observed: diamagnetism and paramagnetism. So diamagnetic substances are repelled by the magnetic field, while paramagnetic substances are attracted. So the substances which get attracted by the magnetic field are called as paramagnetic substances, and those substances which get repelled by the magnetic field are called as diamagnetic substances. Some substances, they get strongly attracted by the magnetic field, and they are called as ferromagnetic substances. Example: iron, cobalt, nickel, etc. Always remember, paramagnetism arises only due to the presence of unpaired electron. If any substance, if it is showing paramagnetism, means what? Definitely it will contain at least one unpaired electron. Okay, it could be more also. At least one unpaired electron should be there in order to exhibit the property of paramagnetism. With respect to the electrons, so which revolve around the nucleus in an atom, so we notice, we observe two types of momentum or motion. So electrons spin about their own axis. So such motion of electron, it is called as spin angular momentum. So here electron spins about its own axis. So such type of motion by the electron, it is called as spin angular momentum. And you know that, so in an atom, electrons revolve around the nucleus. So this kind of motion, it is called as orbital angular momentum. So these two are very important. Calculation of magnetic momentum. See, whenever we calculate a magnetic momentum of any ion, we have to consider the number of unpaired electrons. So based on which we are going to calculate the magnetic momentum of ions. So here we use the formula called as spin only formula. So just now you have come across with the orbital angular momentum and spin angular momentum. Here we are going to consider only spin angular momentum but not orbital angular momentum. Hence the formula used here, it is called as spin only formula. Why it is so? Because when we move from left to right in any transition series, what happens to the atomic radii? Atomic radii keeps on decreasing because of increase in the effective nuclear charge. So when the atomic radius decreases, that leads to the effective quenching of orbital angular momentum. That is why we consider only the spin angular momentum. Here is the formula. Mu is equal to square root of n into n plus 2. So here n refers to number of unpaired electrons available and mu refers to magnetic momentum measured in terms of Bohr magnetons. It is denoted by Bm. Bm refers to Bohr magneton, which is the unit of measuring magnetic momentum. A single unpaired electron has a magnetic moment of 1.73 Bohr magneton. So let's solve some problems in order to understand this. Calculate the magnetic momentum of a divalent ion in an aqueous solution if its atomic number is 20. Here we need to find out magnetic momentum of a divalent ion. That means its valency is 2, having plus 2 as its oxidation number and its atomic number is 25. If you look at the periodic table, which element's atomic number is 25? Definitely it is manganese. So then if we write the ground state electronic configuration of manganese, its electronic configuration can be written as argon core 3d5 4s2. Whenever we write argon core, we are going to accommodate 18 electrons. 25 minus 18 is 7. So first we have to fill the 4s orbital completely. So 2 electrons goes to the 4s orbital and remaining 5 electrons goes to the 3d orbital. Here we have to find out the magnetic momentum of not Mn atom, Mn2 plus. So when Mn atom becomes divalent, that is Mn2 plus, then the electronic configuration is given by argon core 3d5 4s0 because it has lost 2 electrons present in the 4s orbital. Hence the electronic configuration becomes argon core 3d5 4s0. Now in the 3d orbital we have 5 electrons. These are the 5 degenerated d orbitals. So this can be represented as d xy, d yz and d xz, d x square minus y square, and the last one is dz square. So here how many electrons do we have in 3d orbital? So we have 5 electrons. So now electron in each of these 5 degenerated orbitals of d. So first electron goes here, second electron, the third electron, fourth electron, and this is the fifth electron. So then now how many electrons here now? So 5 electrons have been accommodated here and there are 5 electrons in the 5 degenerated d orbitals. What does it mean? Our n value is 5 because n refers to number of unpaired electrons. So the n value is 5. Substitute this n value in the formula mu is equal to square root of n into n plus 2. So then we get by simplification the answer as 5.92 Bohr magneton. Let's take up one more problem. Calculate spin only magnetic momentum of Fe2 plus ion whose atomic number is 26. So first we have to write the ground state electronic configuration of iron, whose atomic number is 26. Then its electronic configuration can be written as argon core 3d6 4s2. Okay, then we have to find out the magnetic momentum of not Fe, Fe2 plus. So then for Fe2 plus ion, the electronic configuration becomes argon core 3d6 4s0. So here now it has lost 2 electrons present in 4s orbital. Now we are left with 6 electrons in the d orbital. Now let's pause on. So here I have got the same 5 degenerated d orbital. How they are named? D xy, d yz, d xz, and then here d x square minus y square, and then lastly d z square. So then now 6 electrons are there. Let me accommodate the electrons. First, this is the second, third electron, fourth electron, and this is the fifth electron. Still we are left with one more electron, that is 6. So then now how many number of unpaired electrons are there here? Just 4. This is 1, 2, 3 and 4. So now the n value is going to become 4. Okay, so never just by looking at 3d6 never come to the conclusion that n value is 6. No, you have to accommodate the electrons. Okay, then only so you will come to know. So then now the n value is 4 because there are 4 unpaired electrons here, and then this is the formula, mu is equal to square root of n into n plus 2, and if we substitute n value here we get 4.89 Bohr magneton as the answer. So this is important for 2 marks as well as for 1 mark. Sometimes just formula alone will be asked for 1 mark, and most of the times they have asked question on solving this kind of problem for 2 marks. The next important property is formation of colored compounds. See, the most of the compounds of transition metals are colored. Colored compounds are formed due to the presence of unpaired electrons which undergo DD transition. See, if any transition metal is forming colored compound, definitely the metal ions of the metal, it should have unpaired electrons. See, color arises only due to the presence of unpaired electrons which undergo DD transition. What is this DD transition? Now we shall see. So this is the splitting of octahedral field here. This is octahedral field OH, and then here it is the tetrahedral field. So here in the octahedral field it splits up into EG and T2G. In the tetrahedral field it splits up into T2 and E. So here in the octahedral field, T2G is the lower energy d orbital and EG is the higher energy d orbital. In tetrahedral, E is the lower energy d orbital and T2 is the higher energy d orbital. Then now here when d orbital splits up into 2 energy levels, suppose if it contains an unpaired electron, so that an unpaired electron will be transferred to the higher energy d orbital. So this is actually called as DD transition, excitation of electron from lower energy d orbital to the higher energy d orbital. So this kind of the excitation of electron, it is called as DD transition. It happens only when there is a presence of unpaired electron. So transition metals they generally absorb a portion of visible light for the excitation of electron from a lower energy d orbital to a higher energy d orbital, and thus compounds are colored. See, so when visible light is made to pass through the transition metal compounds, so then during which they absorb a small portion of visible light. Visible light is comprised of many colors, just like rainbow colors if you remember. So then they absorb a portion of visible light in the form of the photon energy for the excitation of electron, because electron should be excited from lower energy d orbital to the higher energy d orbital. So this leads to the formation of colored compounds. The color observed here corresponds to the complementary color of the light observed. What does it mean? So the color of the compound formed depends upon what color has been observed so in the visible region. So when they are going to observe a portion of visible light, so the color observed by these the compounds so will be deciding factor so for the color of the compound which is formed here. So that is why we say the color observed corresponds to the complementary color of the light. So that means, so visible light has all the colors of the rainbow. Okay, so when they are going to observe a small portion of it, which color has been observed, that color will be the compound which is formed its color. Then the frequency of light observed depends on the nature of the ligand, nature of the metal, and the geometry of the complex. See, so when they are going to observe energy, okay, in the visible light region, they are going to observe in certain frequency, right? That frequency of light observed depends upon the nature of the ligand. Okay, so here the nature of the ligand in the sense means, so ligand is like it may be ion or any group of the atoms which are actually attached to the central metal. Suppose if this is going to be Fe, just a minute, I'm going to select the other color. Okay, so here, if this is the central Fe atom, then it is surrounded by or attached to the 4 Cn groups. Okay, so here Fe is the central metal atom, whereas all the 4 cyanide groups which are attached here, they are called as the ligands. They are called as ligands, which may be either a group or ion which is directly attached to the central metal atom. So its nature also plays a very important role in deciding the frequency of light observed, because the nature of the ligand, the nature of the metal, and also geometry, whether it is octahedral or tetrahedral geometry of the complex. So all these three, they are going to be the factors on which the frequency of light absorbed depends. So here, so I have mentioned some examples of the compounds which are formed. So in the form of the complexes having different colors. Hexa aqua titanium 3 complex is going to have purple color. Hexa aqua ferrous sulfate is going to have green color, and the copper sulfate pentahydrate is blue in color. All these are because of the presence of unpaired electrons which undergo DD transition. Upon this topic, so you will get a question like this: Ac3 plus ions are colorless, whereas vanadium 3 plus ions are colored. Let us see the answer. First, we have to write the ground state electronic configuration of scandium. So, whose atomic number is 21. Then, its electronic configuration can be written as argon core 3d1 4s2. For Ac3 plus ions, so losing all the 3 electrons present in the outermost shell, its electronic configuration is going to be argon core 3d0 4s0. Both in 3d and 4s orbital, no electrons at all. So ground state electronic configuration for vanadium is given by argon core 3d3 4s2. When vanadium becomes vanadium 3 plus, that means losing 3 electrons from its outermost shell, it will have 2 electrons in its 3d orbital. So then its electronic configuration can be written as argon core 3d2 4s0. So what does it mean? So here in case of vanadium 3 plus, so here it is going to have completely empty 4s orbital, but 3d orbital has got 2 electrons. So here, because of having this 2 electrons, it is going to undergo what? DD transition. But in case of Ac3 plus, it doesn't happen so. Ac3 plus ions do not contain any unpaired electrons. DD transition does not take place, hence they are colorless. Whereas in case of vanadium 3 plus ions, they have 2 unpaired electrons, hence they undergo DD transition. Therefore, vanadium 3 plus ions are colored in nature. Complex formation. Transition metals form a large number of complexes. This is due to their smaller size, high ionic charge, and having vacant d orbital for bond formation. So these are the 3 reasons why transition metals form a large number of complexes. Here are some examples actually I have mentioned. Hexa aqua titanium 3 complex, hexa aqua ferrous sulfate complex, then copper pentahydrate. All these are examples for complexes formed by the transition metals. Next very important aspect is catalytic property. Transition metals are very good catalytic agents. That means so they can be used as catalysts in various reactions. Then what are the possible reasons for this? Ability to adapt variable oxidation states. See, after losing electrons present in 4s orbital, so these transition metals can lose further electrons from inner 3d orbital. So because of this, not only they can increase their valency, but also they can increase oxidation states. So this property is one of the reasons why transition metals can be used as catalyst in various reactions. The second reason is the presence of vacant or partially filled d orbital. So this is also very helpful in the formation of the bonds. That is why they can be used as catalyst. The last reason is they have a tendency to form complex compounds. Already we have discussed about this. So transition metals, they form a number of complexes. This is also one of the reasons why they are widely used as catalysts in various chemical reactions. Next is formation of interstitial compounds. If you look at these pictures, so what you can see, it is nothing but the array of the atoms in a repetitive manner, which is called as crystal lattice. So here, between the atoms there is a gap. Such gaps are called as interstitial voids. Transition metals, they have a unique property of trapping the small atoms like hydrogen, carbon, nitrogen, etc. in these interstitial voids of the crystal lattice. Such compounds formed by this the process, they are called as interstitial compounds. For example, titanium carbide, iron hydride, manganese nitride. So these are the examples for the interstitial compounds. So where transition elements, they are going to trap hydrogen, carbon, nitrogen in their interstitial voids to form interstitial compounds. Then what are the characters of these interstitial compounds? They possess four important characters. They have high melting point. They are very hard in nature. They are chemically inert, and lastly, they retain metallic conductivity. So even after trapping the small atoms in their interstitial voids, they retain their metallic conductivity. So here in this topic, so you will be getting a 2 marks question like what are interstitial compounds? Give an example. So you need to write the definition with an example. Next important the topic is alloy formation. A blend of metal is called as an alloy. So when we mix two or more metals together, we are going to get alloy. So which is obtained by mixing two metals form a large number of the alloys. This is because of their similar radii. So when we discussed about the lanthanide contraction, so we have studied that the atomic radii of second and third transition series elements are virtually the same. So because of the property of having similar radii, it is possible to produce alloys from them. So alloys which are formed by this process are very hard and they have very high melting points. Here are some of the examples for alloys formed by the transition metals. So brass is formed by mixing copper with zinc, bronze is formed by mixing copper with tin, and steel is an alloy of iron with manganese, nickel, chromium, molybdenum, etc. So that's it for today. So we shall meet in the next class. Thank you.